For example 12.27, it says determine the radius of barium in picometers, given that it forms a body-centered cubic crystal structure with a density of 3.59 grams per centimeter cubed. And for body-centered cubic unit cells, we use this equation to calculate the edge length using the radius. So this is kind of going completely backwards from the previous question. In the previous question, we started with the radius in picometers, and we had to calculate the density. Now we just got to go backwards from density to radius. How are we going to do that? All right, so they gave us barium. We need to know what is the molecular weight of barium. So barium, I think it's 137, if I look at the periodic table of elements, 137.33 grams per mole. And it's also important to know that in a body-centered cubic unit cell, there are 2 atoms per unit cell. So if I want to get this to grams, I'm going to need to do the same method as before, so 1 mole divided by Avogadro's number. And then I'm going to multiply that by the molecular weight of barium. So I can cancel out atoms, and I can cancel out moles. So I'm left with 4.561 times 10 to the negative 22 grams per unit cell. I'm trying to get to centimeters cubed by itself because that's what I need to use to figure out the radius by itself. So I can cancel out the grams because I want grams on the bottom. I'm going to put the density, I'm going to reverse it. I'm going to invert it and put 3.59 on the bottom. So I'm left with 1 centimeter cubed on top. Because if you multiply them together, then you would just be getting grams squared, but we're actually trying to get rid of grams. So I'm going to put a 1 underneath, so at least now everything makes sense. And if I cancel out the grams, I'm left with just centimeters cubed by itself. So that's going to be 1.27 times 10 to the minus 22 centimeters cubed. So we're trying to go from centimeters cubed all the way to picometers of the radius. So before we do that, we need to understand that centimeters cubed is equal to the edge length cubed, because that is the volume. So we need to figure out what is the edge length so we can then plug it into that equation and calculate the radius. So volume equals the edge length cubed, and that is 1.27 times 10 to the minus 22 centimeters cubed. How do I get centimeters by itself? Well, I'm going to need to cube root both sides to get rid of that cube. So if I cube root this, it's very important not to square root it because square rooting would give you a very different number. You have to cube root it. You have to make sure you have that 3 out front for this to give you an accurate number. And if you need help with your calculator, either use YouTube or Google or contact me and I could help you figure out how to do a cube root. But it's very important not to do a square root. They're very different. So a square root is when you're halving it to the x to the 1/2 power. A cube root is to the 1/3 power. So if you don't know how to do the cube root function, if you just want to do the caret function to the 1/3, it gets you the same value. All right, so when I plug this in, I get an edge length of 5.03 times 10 to the minus 8 centimeters, because I also cube rooted my centimeters. And now I can actually use that edge length equation is equal to 4r over the square root of 3. And I want to figure out what is r. So how do I do that? Well, we're going to have to use basic algebra. I'm going to multiply the square root of 3 on both sides. And that gets me 8.712 times 10 to the minus 8 centimeters equals 4r. So now I just have to divide by 4 on both sides, and my radius is equal to 2.178 times 10 to the minus 8 centimeters. So the only thing left to do is to convert our radius from centimeters all the way to picometers. Okay, so my radius is 2.178 times 10 to the minus 8 centimeters, and I want to get it to picometers. So how many centimeters are in a meter? Because I like to go to meters first and then picometers. So I want centimeters on the bottom so they can cancel, and I want meters on the top. There are 100 centimeters and 1 meter. And then how many picometers are in 1 meter? There are 10 to the 12 picometers. So it's really important. This always trips up students. You can type in your calculator 1 times 10 to the 12th or just 10 to the 12th. It's important to do it like this because if you type your calculator, you have to use an e for the time. So that'd be 1e to the 10 to 12th. You can't do it like this. You can't type 10e to the 12th. It would give you a very different answer. So when you're working on your calculator, you can type in 10 caret 12 or 1e 12 when you're doing your calculator. All right, so the centimeters are going to cancel, the meters are going to cancel, and I'm left with 218 picometers. So you're not really going to see problems like this very much because of how lengthy they are, but they're really good practice to make sure you have your math down. Since General Chemistry 2 is a very math-intensive course, this is a very fun problem to just make sure your algebra is correct, you know your conversions, and you can go forward, backward, backward to forward. But don't expect seeing this one that much. So we've discussed the unit cells for metal solids. Let's go into a little bit of ionic solids. Ionic solids consist of cations and anions. I want you to get really comfortable knowing those words. So the cation means it's positively charged, and an anion is a negatively charged ion. Cations are typically much larger in size than anions. Not always, but majority of the time. So an example of the opposite of this is sodium chloride. So remember where they are on the periodic table of elements and how the trend goes. The size goes larger as we go left and larger as we go down. So sodium is going to be a little bit smaller than chloride. So the larger chloride ion adopts a face-centered unit cell arrangement. And then the sodium ions occupy the spaces between the chloride ions and are also in a face-centered arrangement. But what happens if we compare it to cesium chloride? So we have sodium, which is higher up on the periodic table of elements, and then cesium is on that same column. It's just at the very, very bottom. So in size, you have sodium, and then we're going to have a very big cesium. So the cesium is going to be a lot bigger than those chlorides, so they're going to have a lot more space if chloride doesn't change in size. So let me show you a picture. So here's a figure of sodium chloride. So they're much closer in size than cesium chloride. So chloride is acting as the corners and the faces, and there's also one in the center. Whereas sodium, which is slightly smaller, is going to be on the edges. So remember that edges are 1/4 of an atom, and since there are 6 edges, it just depends on how many there are on the edges. So it just depends on where it's at. So sodium plus, sodium plus, sodium plus. So it looks like this is a lot more dense if you compare it to just something that's a pure substance. Now let's look at cesium chloride. So cesium is much larger than sodium. So the way that it's going to pack efficiently, you're going to have the cesium in the middle, surrounded by the chlorines on the edges. So this one's not going to be as densely packed as sodium chloride. So if I compare them, which one's going to have the higher boiling point and melting point just based on those densities? Sodium chloride is going to have a much higher boiling point or melting point just because it's more densely packed. So it's going to take a lot more to overcome how close all the molecules are. So if you just compare those two, sodium chloride is going to have a much higher melting or boiling point.